Thank you, Mr. Deutsch. It's been a pleasure to coming back here. It's seeing those old faces and, of course, the new generation. So, I mean, I've been sitting on your chair 2000, oh my God, at least 11, at most 11, 2009 to 2011. So this would be a mixture of motivation talks and because we are in a mathematics seminar, so that's going to be mathematics. So that could be both, because we do have a spectrum of audience here that are both interested in both tail of the spectrums. So without further ado, let's go into the outline of the talk today. We will obviously hit some introduction, some kind of notational backgrounds that are needed to understand the general topics. We will kind of put the maps of where this research area is at, why it has been has created, and where is it at today. Bullet 3 and 4 are the two most traditional methodologies that are used to analyze those type of problems or network. 5, 6, and 7 are contingent to, depends on the time and the interest of the audience, and then we'll go to the conclusions. So before I'm going further, let's ask ourselves those type of 4 questions. So this is the kind of questions that I started to ask myself since I began to go into this research area. I kind of substitute the first questions with what type of problem can be modeled as a network or a graph. And by asking that questions, I would like to see if there's anybody's in here that are actually using some sort of social network. Anyone? Raise your hand, please. Facebook, LinkedIn, you know, as I exhaust the entire Twitters. Okay, all right, so more than 70%, 80% of the room pretty respectively. We're all part of the network, believe it or not. In terms of social network, if we think ourselves as nodes, so each individual is nodes in the network, our connections is actually where we are making Facebook friends or LinkedIn friends or connections, professional network. That's where an edge is drawn in the network, right? If you look in your Facebook app right now, especially in the friend suggestions portion of it, you would have a couple of suggestions that are ranking all the way from the left to the bottom to the right. Have you guys ever asked yourselves the questions, why do it's ranked a certain way, but not the other way? Why do this person are showing on the most left and the other person are showing all the way to the right of the scroll in your friend suggestion?
How the number of mutual friends?
1 parameters, mutual friends. Physical locations, the 2 persons that are sitting next to each other. That's why it's, you know, I think privacies and things like that are very important for social network companies, because if that is considered one of the parameters that could goes into whatever the model that we are using, it could alters the order of likelihood of forming an edge between 2 nodes in the network, or forming a connections between 2 individuals or social network users. So those are the type of problem that can be modeled using graphs. And the graph and networks are analogous terminologies in a sense. And not only social network, the World Wide Web that are formed from the 1990s can obviously also be modified or be modeled through the term network or graphs. Biological networks, the relationship between different entities, different generations, all of those can be formed using network. So conclusions is network is everywhere. And with the birth of social network, this type of research area becomes one of the hardest research area that as far as I'm concerned, that we are involving in this time. So the next question is if we agree that is pretty hot topic right now, then how do we present that? And obviously, if we said that we present it through a graph, a two component of a graph is the node and an edge, right? So number 2 is pretty straightforward. So number 3 is what we were talked about today, the idea of community. We already talked about 4, why it has been a pretty hot topics for research right now. We talked about number 3 as we unveil the contents of this seminar later on. But before I do that, I wanna ask your opinions on what do you think as a community? Any idea? Quick idea? What is community in network? Or in terms of social network, what is community?
A group of like objects, I guess, that are associated through certain variables. I don't know.
Yeah. Yep. So why don't Facebook suggest somebody that are randomly in California through your Facebook account, but somebody that are sharing common interests with you, movie interest, whether it's movie interest, somebody that you follow in Twitters, somebody that you are mutual friends with. If those are the things that you have nothing in common, the algorithm is still gonna suggest somebody very randomly because there's always a random factor into a model, right? In other words, you don't even know that you want to make the connections with a random person, do you? Sometimes you don't. That's called a damping factors, right? So they want to, in model, we generally want to taking into the random factor into account because we don't even know the human behavior sometimes, right? So those are the things that we start to unveil it. So you're right, I think that's exactly what's the idea of how we think the community in network looks like or how it's formed. This is the official mathematical sort of definitions or formation of communities. So if we agree that members in networks are nodes and connections are edges, vertices are another terms for nodes, right? So vertices, the vertex that are densely connected amongst each others and sparsely connected with the rest of the network are a community. Now, very important, this is just a definition. This is not the definition. This is one of mostly used definitions that they are agree. Nobody know for sure with 100% agreement across the research spectrum that this is the correct or mathematically rigorous or socially rigorous definition of community, but this is one of the most commonly used. So as you can see here, those is the idea of the formations of communities in network. So like you said, a group of people that are following the same type of persons or like the same page or going to see the same movie and checked in the same place and going to the same school and having 25 people that are having in the mutual friends, for example. That's one definition, okay? The cardinality of rho is more or less, the rho is a set of collections of communities. Vi is the collections of vertices that are in community I, okay? And the sum of Vi obviously gonna recover the entire network, which is the cardinality of vertex, which is V. So V is the entire thing. Vi is this, for example. Obviously, edge that are edged up in each communities are obviously gonna exhaust the entire network as well. So you can see that it's recover the total number of edges in your network, right? Or in the social network sense, it's the total number of connection that one has. Or in the graph theory sense, it's definitely the degree of a vertex, right? So if your Facebook account has 600 friends, obviously your vertex has a degree of 600, okay, in the graph theory sense. So that's more or less a transitional from a very application standpoint to a mathematical standpoint. Okay, so this is a lot of information, I know, but this is all the most of the common methods that have been developed during the time that social network and network science has become a research areas. So as you can see here, I want you guys to pick out some of the words that we familiar with. So something like matrix. Okay, matrix might be the only thing. Graph theory, Markov chain, information theory might be. Subspaces is for those who are taking DiffyQ, right? You know, subspace, you know, the node space, the left node space, all that for fundamental subspace in linear algebra. So those, when you start to pick out those familiar terms, you will see that there are certain connections between network analysis and Calc 4, okay, especially on the linear algebra side of it. And yes, that's exactly what we will be doing. Of course, there's other methods as well, but that's not part of what we will be discussing. It's mostly because of the irrelevancy of the methodologies with respect to the audience. Okay, so let's talk about a little bit about the question, why now? I think those are the four most anchoring reasons that network analysis and network science has become very, very hot today. First is the availability of supercomputing power. If you guys are having come up with an algorithms that can, that you think on the theoretical standpoint would successfully analyze the behavior of a network, the computer can do it now in what's called a polynomial time, which means that you don't need to wait theoretically forever to see the results, whatever that analysis might be. Back in the day, it's kind of a fancy thing to do because we don't have such power to do it. The born of the World Wide Web, I mean, in 1990s, that's kind of where everything are kind of took up. The research of network has been established in the 30s from a social standpoint, but actually when we started to use mathematics into the analysis of such network is not until the 1950s, and then the 1990s is where the blooming of the World Wide Web is really where it takes up. And of course, you know, in the 2000s, social and biological network are start to become, you know, things that we all involve in one way or another. And this is really important because of the improvement of scientific approach and scientific technologies. I think these are very important because the data set that we have now is not only rich, but also very accurate, at least in the terms that much more accurate from the data set that we can be able to afford before. So those are the things that I think resonates in the research area and really help to grow this research area. I really like it, this terms or this saying. So it's not really from anybody, but it's just from my personal opinion. The two persons that are sitting next to each other right now might not be the two the nodes that are in the same community, right? From the randomness standpoint, I mean, the two persons come from two different states, registered in the same class, sitting at each other. Euclidean and distance-wise, very close, right? Not necessarily mean together. So those are the things that one has to be really conscious on in terms of network science and network analysis. And I'll give you a very cool example at the end of what I mean by that. I will collaborate more on this. But just keep that in mind as we go along. So when we analyze a network, there's certain things that we need to consider. There's methods that all it cares about is about the weights or the significance of connections between two nodes or two members, which means that how tight you are, how close you are with the other person, it can numerically represent by a number. And that number may be a 0 to 1 or any other sort of scale that one wishes to use. In the area of what I will be working on at Purdue is actually the human brain connectomic network. So I can represent the relationship between two different areas of the brain by how close they are in terms of doing a task. And that can be represented by correlations, coefficients throughout different time series and all that good stuff. So in social network, you can define how close you are with another node or another person through how many things that you have in common, for example. That's up to you how you define it, okay? And you can scale it whatever, according to whatever methods that you wish to use. So it's very generic, and we have to keep it that way. There's methodologies that are strictly considering the dynamics of network. So network is really time-dependent object, right? I mean, you can friend and unfriend a person, and all the time. I mean, you add another person, and then you unfriend another person. You follow a page, and then you unfollow it. It's very common. So how are those change in network affects how good you are at detecting communities, right? I mean, for example, if I'm a person in the network and one day that I decided I'm not a fan of the current community that I'm on anymore, I decided to unfriend all of my friends and I want to move to Hollywood, for example. I'm now in a different community, and then how the networks reacts to that, or how the methodology reacts to those changes is going to be determined how good it is, right? So those are the things that also we need to consider beside the Euclidean distance or the how far we are apart from each other. So with that being said, now we're going to move to the first methods that I think most relevant to the audience today. It's called the Louvain method. And basically the Louvain method is one of the first methods in network analysis. It's basically put the two nodes that are, it's all it cares about is if the group of nodes that having a very closely or dense connection with each other, they'll put it in the same kind of communities, okay, very simple. So if two persons are having the same type of connections or the page that they liked or things that they do, it represented by the weight. And if that weight is large enough, the Louvain method will eventually put the group of nodes or that collections of people into a group or community. So go back to the previous point that I made before. When you analyze those things, you can consider an aspect of it. And the Louvain method consider the weight between two people, okay? It follows very, very closely to this sentence. It says that community respects the density of vertex connectivity. When it's close together, I put you in the same group. Is that necessarily true all the time? No, but that's one way to do it. Because we don't have a universally agreed definitions on what community is. That's one way to say it, right? The closer, the better. That's where everything started, I guess. And the Louvain method, a little bit of the story on that. The Louvain is actually a university in Belgium, European. And apparently, I think Northern European and the southern part of European are very well known in network science. By Southern European, I mean countries like Spain or Italy. In the Northern, or even mid-European, excluding the area of Hungarians and stuff like that, countries along those lines, I think very strong in network science. And the people and the person, I don't know how to pronounce it, so I'm not going to pronounce his name, but he actually started this method in his master thesis, and then the Louvain kind of, take it to another level of making publications out of it and having professors that are involved in developing the methods and stuff like that. But really, the original credit should go to that person who are getting things started. The Louvain method are later on being commended and praised by a lot of others, authors that have worked on the idea of what's called a modular network science. Being modular stands for modularities or communities. These Lambaudier are also very big researchers in network science. So this is the mathematical part of it, okay? So this, in every single method in network science, you're gonna have some sort of objective function that you're gonna optimize. Whether it's a score, so for example, if you wanna put a score, a group of people that are densely connected with each other, you wanna raise that score up, right? So your goal is to put the group of people that are densely connected to each other. So this is the Q function, is the function that keeps track of a score and how good you are at putting a group of nodes into one community. And I will explain the terms here, so no worries at all. M is the total numbers of connections in your network, okay? So obviously 2M stands for, if one have taken graph theory, 2M is equal to the number of degrees in the network, okay? IAJ is the adjacency structures of network, where I and J is just the node index. So you and me and whoever that are taking part of the network is I and J. It obviously runs from 1 to the canality of the network. So maybe the network has M node, or N node, for example. I go from 1 to N, okay? And the same thing goes for J. Make sense? So that's what it means. So if I have a connection with you currently, and I'm maybe number 37 in the network, you 41, I of 37, 41 is 1. So adjacency structure is always a 0, 1 structures. Either I make a connection with you, or I don't have a connection with you, that's it, okay? Pij is the probability of me making the connection with you, fair enough? And that could be measured to whatever parameters that one decided to use. The only thing that are required for us is the probability has to be from a number between 0 and 1. It could be measured from the number of common friends that we have, things that we like, place that we checked in, whatever the parameters that we decided to use that go into the analysis, okay? If everything that I do is the same thing as everything that you do, theoretically, P should be 1. Because I want it to be it's approaching, right? So on a theoretical sense, it's approaching 1, right? But is it approaching 1 on reality? There's randomness factor into it. I can do the same thing that you do, and you and me have absolutely nothing in common. It's just out of random. I can go to the same place that you go. I can do the same thing that you do, checked in the same place that you checked in, like the same page that you like, have the same friends that you have, but I don't know you. Does that realistically make sense? Probably not, but theoretically does, right? Because it's just converging to 1. It's not 1, right? So there's that idea. The delta here is what's called a Kronecker delta. It's basically saying that if me and you are being in the same community, GI and GJ is the same. Remember that rho at the very beginning that we have. Rho is a set of community that we have. We're in the same community. If we're in the same community, the Kronecker delta is 1. Otherwise, it's 0. So this is intuitively, it's a score function, right? If me and you in reality does have a connections, and probability says that we are more than likely you'll be friends with each other, these scores would be what? Very close to 0. If they're close to 0, and this is 1, it would count it as a sort of a score or grades, right? This we don't know because this is theoretical aspect of the model, right? When you say probability, you are trying to model potential relationships. This is actual relationship or AKA the no model, right? Where things are either yes or no. But in network analysis, we critique the methods based on how good the methods recognize community structures. Because in reality, we don't know this. All we can do is assume or actually study the network and then understand the actual connections before we use methods like this to calculate or to partitions the network into different communities. So not so bad, right? Very intuitive in terms of objective functions, right? Yes?
If that's close to 0 when the probability is close to the actual, why do you want to maximize it?
So that's a very good question, because if whatever information that I have is limited, this would drive this probability measure down. And if with the limited measures, and I actually identified it correctly, this difference would be large. And I want it to be big, because if I can drive it to be big, on the theoretical sense, because this is information related, right? If you have less information, this measure would be low. You see what I'm saying? And
So
it's
you want that to be low in order to maximize Q.
you don't always have the luxury of knowing that to be low or not. But this really depends on the time as well. But I ignore the temporal aspect of the model for the time being, because it would just adds up the complexity of what we're trying to do. So let's just assume that it's time independent for a moment. So we have less information, and we actually do have true connections. It would drive that objective function up.
I see. So you want to maximize the ability to, with less information, maximize the actual connections.
Yeah, yep. And
So you don't
the
need
more,
as much information in order to still have an accurate connection.
that determines the goodness of your methodologies. Yeah. So some of the pros and cons. Like we mentioned before, it puts things that are densely connected to each other. It follows the definition, but it didn't consider how it flows, how information flow in the network. In other words, it's only gonna consider that network at that point in time, and that's it, right? But we know that network is much more dynamic than that. So that's what the good thing about this is, it's gets everything started, right? Where this is right now, because this is essentially what started the whole thing on modular network science. A lot of people have been doing research in the variant of this model, and it would take it into a directed network case. This is obviously, like one can see, is undirected, which means that I can be friends to you, and that means that already implies that you are friends of mine, right? Directed network is different stories, right? Would have directions and go from U to V. I might be wanted to be friend with you, but the other way around might not be true. And so it adds up the complexity of the analysis. There's a lot of variants of the Louvain methods as of today. So that's where it's at. Okay, so then the next one that I want to talk about is really builds that definitions and foundations for us. This is the methods that are developed from a physics professor from University of Michigan, 2007 2006. It actually started in 2004, but the paper that are being said and done and published are in 2006 kind of range. His name's Newman. So it's basically looked at the same idea. But before you can see that, when you go Aij minus Pij, it's more or less going term by terms. It does not set up the problem in the matrix kind of fashion, right? So Louvain, what he did in the nutshell is sets up the same sort of objective function in the matrix, okay? So what does that mean? Before we go to the matrix, I wanted to also emphasize what he's trying to optimize. So the things that are in common about network analysis or modular network science is that you always have objective function that you want to optimize. And this is the objective function that Newman trying to optimize. It's 1/2 of Aij, where I and j are going from 1 to 2. Okay, so there's two problems with this. Number one, I and j, the first one, the one I'm about to say is not really a problem, but one should point out clearly that what it means. I and j is no longer stands for node index. Okay, it's no longer from 1 to n. I and j now is the community index. Okay, so it's either 1 or 2. Fair enough. That's why it's always go to 2. Okay, it's not going to n. Sum of I and j, where I and j is in different community, that basically counting how many edges that one make when you are in community 1, but you have friends in community 2. Sounds good? You see my point, right? This is community 1, community 2. This is what we're counting here. We're not counting this or that at all, okay? All we count is this. And the reason we count that is that this shows how bad we are doing with our partition. Because what it says is that if you are a member in the community 1 and you make some connection with the other community, which community should you be in? Okay? True, that depends on the information that we have. So if you make more connection with this community, it makes sense for you to be in this community, but it doesn't restrain you from making friends with the other tier or other communities. Yes?
So in the diagram you had way back where you had a number of communities.
Yep.
One thing I noticed is they were all mutually exclusive. Is that a requirement?
No.
That's correct.
No. There's algorithms that are detecting what's called the overlapping communities. But of course, that is much harder to do. Exclusive community detections are basically cut the networks or cut the graph in a very clear manner. So if you belong here, you don't belong there. That's it. End of story. So those are the basic models that one can consider. So we don't get into these type of situations where you have connections with the other members in other community, but which community should I put you in? That decides this. So as one can see, this goes back to the original definitions of we want to have dense connection within community, but we want to have sparse connections with the other community. That's why it needs to be minimized, right? Okay, and then this is the considerations where the total probability measures is the same as the total number of nodes or edges that we make is equal to the total of 2m's. And this is a basic assumption to just ease or to relax our analysis. And of course, P and A is again adjacency structures versus probabilistic structures of connecting between two numbers or two nodes. Okay, so A is adjacency structures. S is the 1 by n vectors that are either a 1 or a -1. It's a 1 if it's in the first community. It's a -1 if it's in the second community. That's it. Okay, simple enough. Anyone familiar with this, right? The inner product? Okay, so this, because S is a 1 by n vectors, so add dot with itself is n. Basically, 1 times 1 is always 1, and -1 squared is always 1. When you add up through the entire array, you would recover the number of vertex. So this is very smart of him to define this vector that way, and we'll show the reason why. You do not need to be worried too much about this, but for people that knows linear algebra, this is the incidence matrix. This is a rectangular matrix, not a square matrix. It basically shows the relationship between a node and an edge. So you got the nodes in the row, and you got the edges in the columns, and it shows the relationship between the nodes and edges. So if the node is involved in an edge, it would have a -1 in the tail, and the 1 in the head. Very easy, but that's M. This is what we want to pay attention to. This is called the Laplacian matrix, and the Laplacian matrix is basically the product of M with M transpose. And the reason that we do this is because we want to get rid of the edge. We want to get rid of the M. We only want connections or relationship between the nodes with the nodes. Okay? All right. So the only thing that I want you to remember is that the Laplacian is a square matrix because it's an M by M matrix. There's another way we can calculate the Laplacian. So one way is obviously doing that, but the other way is the Laplacian is equals to the degree matrix minus the adjacency structures. So the degree matrix is the diagonal matrix, which means that everywhere, every entry that off the diagonal is 0, and things that are on the diagonals is how many connections that you make with the network. So if you make 600 strands, your degree is 600, right? And that represents that. So if you take D minus the adjacency structures, you would also get the Laplacian as well. But the reason why I want to show the incidence matrix is for the professors that are familiar with linear algebra is actually called, the Laplacian is actually in the quadratic form, and AKA the Cram matrix. The Cram matrix is very nice is because not only that it's in the quadratic form, but also it's symmetric, which means that whatever in the diagonal up here, you would see the exact same information down the diagonal. And it bears a lot of tremendous advantages in analysis later, as you can see. Okay, so this is where a lot of mathematics is going to be thrown at you, like it or not. Remember the vertex, the array S before? It's 1 by n, it's either 1, -1. Guess what? It's in the span of the Laplacian's columns. Okay, so basically, all it says is it's a subspace of a Rn by n. Okay, when it is a subspace of an Rn by n, you can use Gram-Schmidt or any other techniques to orthogonally diagonalize the Laplacians. Okay, basically what it does is that it's gonna give you a bunch of column vectors that are mutually orthogonal with each other. And if you go back to the R3 and 3 kind of example where everyone are knowing what I'm talking about, so E1, E2, E3, that's this, right? And the reason why it's so efficient in linear algebra analysis is that not only the norm, the Euclidean norm of those vectors is 1, 0, 0, 1 is also only have 1 in one of the entries and 0 everywhere else. So not only the norm is 1, but also those 3 vectors are mutually orthogonal to each other. The same thing you can go for doing a Gram-Schmidt sort of techniques to diagonalize the Laplacian. Because the Laplacian is symmetric, its entry is real, it's a Hermitian matrix, okay? That means that it's fully diagonalizable, which means that you can have a full spectra of the matrix. So then, long story short, I have prepared the proof to prove this, but I don't think we have enough time to go through the proof. So let's just bear with me and assume that this can equals to 1/4 of S transpose times the Laplacian S. Okay, so we basically just use all of the linear algebra techniques to equate this into these equations that are related to S. Okay. Another fact that's so nice about the Laplacians is because it's Hermitians or fully symmetricals, this relationship can be then further written as a linear combinations of lambda i's, and lambda i's is the eigenvalues of your matrix times some sort of constant AI with it, okay? And you want to minimize it, okay? So when you minimize it, by the way, for the real entries matrices like Laplacians, its spectra or its sets of eigenvalues is always real, so which means that the smallest eigenvalues is 0. For any graph, the largest eigenvalues is 2. It's always bounded above by 0 and bounded below by 2. That's true for every graph that you're going to deal with. So of course, lambda 1, if I start at 1, lambda 1 is always 0 regardless with the Laplacians. And one can easily check that. So in order to minimize it, I can say that because this is 0, I can assign a non-zero entries here. And the closest one I can do is 1, for example, and 0 for every other AIs that I see, because I know that every other lambda i's would be non-zero, right? So I want to minimize that. Wherever I see the 0 for lambda I would put the non-zero entries into it. Okay, does that make sense? But then guess what the eigenfunction or the eigenvectors that are corresponding to this lambda 1 is. So this is very important, and if there's something that that you want to take away with this with respect to this, this is going to be it. Lambda 1 is always 0 with respect to the Laplacian. Okay, lambda 1 is 0. V1 is the eigenvectors of with respect to the eigenvalues of 0. It's all 1. And the reason for that is one can easily check because of this reason, that the Laplacian is d minus a. So when you times the Laplacian with the all 1 entries, you would retrieve a 0 times 1, which is a 0. Okay, so that's another structure that is so nice about the Laplacian that makes that always true. Okay, so this is what calls the trivial. So remember the array S, the vector S? We said that it's either 1 or -1, correct? Guess what this is? This is S in a very trivial cut. Everything are in the same community. Because go back to the cut itself. I said that I want to count things that are making its ways to the other community. And so the best cut is what? Is there no cut at all? Is that everyone in the same community, there's nobody that are escaping and going to the rest of the network. So the minimized values of that is 0. Everyone knows it before, that's why it's a trivial cut. That's the best cut. Is that what we want? Obviously not. So when that's the case, then we move to the next eigenvalues. So the next smallest eigenvalues, and obviously there's going to be the corresponding eigenvectors that are corresponding with that eigenvalues. That eigenvectors is, I think that's called like $10 billion eigenvectors, because the person who invented, I'm not sure who found that out is Fiedler, and he has that name. He has his name after that vectors as well. So it's called the Fiedler vectors. It's the second smallest. It's the eigenvectors that are corresponding to second smallest eigenvalue of a graph, okay? All right, so that's just further math, and okay, to say how lambda 1 is 0, and the algebraic connectivity of a graph is corresponding to the second smallest eigenvalues. All right, so I want to use the rest of my time to demonstrate this second smallest eigenvector to you with respect to real network. And I think this is the fact that when students want to pay attention to, because this is pretty cool stuff. Okay, so this is the MATLAB code that I created. It's basically, okay, so it's basically the what's called a preferential attachment model. It's one of the biggest and well-known model to model social network. Social network is basically characterized as an online model. An online model is a model that new members or new nodes always being introduced to the network. An offline model is the number of nodes is always fixed. If you have n members, you always have n members. But the social networks, there's always new members that are coming into the network, right, on a timely basis. So the preferential attachment model is supposed to track when a new members are going into your to the network, what is the connection that it's likely to make, okay? And this is the research project that I'm currently working on right now with another math professors at Western. So we use the basic preferential attachment model, but then we inject the community into the preferential attachment model. So basically we say that when you make a new connections, we allow you to make up to m connections. But we already have our community structures that are established before. So if you are allowed to make m connections with whoever, how many friends that are currently in the network right now, and if you make 6 connections with community 1 and 4 connections with community 2, the algorithm is gonna put you in community 1 just because you are making more friends with community 1. So we say that you're more likely to be in community 1. Okay, so that's how we assign connections. Okay, and is it big enough for you guys to see, or should I? Because I'm not sure how to expand it. So n equals 90. That's basically half of the total members that are currently that you want it to be at. So when you can choose it whatever the numbers you want, the way that I have it set up. So right now the total network that I want to build up is up to 180 members in the network. Every time I introduce a new person in there, I want to make 10 friends. P and Q is the sort of the scale for me to balance, because if I introduce you to one community, I want you to make more friends with the community that I introduce to you, but at the same time I can restrict you to make friends with other communities. That's what Q is for. Okay, so I want you, in this setup right now, I want you to more than 100 times more than likely to make friends with the person that I assign you, but I'm not restrict you to make friends with other person that are not in your community. Is that fair? Because that's how it sets up. So those are the parameters that we use. And let's go through all of the other stuff which you don't need to consider about. Okay. With the parameters that we discussed earlier, so when I introduce a new person into the network, if I introduce it to the red community, for example, I would want you to make more friends with the red community 100 times more than the other ones, okay? And clearly, if the second smallest eigenvectors are doing its job, it should somewhat, at some precisions, identify correctly the community structures. And through my code that I calculate, to a certain point, it predict the community structures very well. But notice that P is currently 100 times higher than Q. So let's do a little bit of experiment and see what happens when P are not so close to Q. So what I changed here is that I changed from 100 to only 3 times more than likely, and rerun the algorithm and see what happens. You see a different phenomenon, right? It's still doing its job. It's still doing the cut. But there's hardly any community structures in the network. It's because when P and Q are so close with each other, there's going to be a point where the Fiedler vectors is not going to do its job of cutting anymore. It's still doing it. But if you look at of how the network is being created, there's almost no community structures in the network. So let's try another one that are, let's see, 150 nodes. I think when I tried it yesterday or 2 days ago, 5 was a pretty good cutoff. Okay, so you kind of can't see the community even because it's only the ratio of 5 to 1. I mean, it's relatively small, right? But you can kind of see that the cut is here, right? It's not a good cut, obviously, because you don't inject a good community structures into the network. But the cut is there because the Fiedler eigenvectors are kind of doing its job. So which means that there's entries in the vectors that are positive, and there's entries in the vectors that are negative. Let's try another one. Let's try 1-to-1. 1-to-1 is very weird because I'm saying that there is no community structures. Let's see how the computer handle that. See a bunch of warnings? It says that the Fiedler eigenvectors is no longer a good partition because you hardly have any community structures. Everything is in one community, right? So otherwise what it says is that the cut cost is extremely high. There's no point in the network that allows you to have a relatively small cost. By cost, I mean every time that you cut through a network, if you hit an edge, that's $1, okay? And that would add up to the total number of edges that go through your cut. You see what I mean? So if I inject the 1-to-1 ratio, I hardly inject any community. As a matter of fact, I don't inject any community structures into my network. And so everyone is in the same community. But when it gets to 5, when it gets to 50, let's try 50 and see if we can see anything like that. Okay. So here you can see that doing a pretty good job. But the cost is high though, right? It's relatively smallest with any random cut. Any random cut would not doing as good as the Fiedler vector cut. But the cut cost is still relatively high. If you go to an extreme case of, I think we tried 100, but let's try 150 and see what happens. Even sparser, right? So the cut is reduced and reduced with the value of P. Let's try an extreme case. All right, so at some point in time, one would expect no community at all. I mean, no interactions with community at all. What I'm saying here is that out of the 10,000 times, you only gonna likely to make friends with the other community only one time. That's what this parameter says, right? I'm not saying, I think this is converging, but I have not proved it analytically yet. No cut. The cut cost is absolutely 0, which means that one can, is in terms of the graph theory, this is two disconnected components, right? So out of 100,000 chance, only one time that it make connections with the other community, which it didn't happen. So, but this is, again, in terms of simulation, you only ran one simulation. So when it ran another one, you might have a different. Okay, probably you're not going to see any cut.
Might be a while.
Yeah, so out of 100,000 times, 100,000 more than 100,000 to 1 ratio is extremely hard to see an edge of connections. So with that being said, that is all I wanted to show today. I would like to, number one, motivate the student of future generations to go into this type of research, and mostly because what you are studying right now in the calc class, you can clearly see how it's being applied in those research. So not necessarily going to be a theoretical development, but also something that are very hands-on, very intuitive, something that would add on to your research career. And if you don't want to stay in academics, you obviously can work somewhere in California, where basically the social networks companies are all there. So Google, YouTube, Ubers, Facebook are all located in California, or even Human Brain Network, that's part of neuroscience, or biological network. Or the opportunities is pretty much endless. And this is to prove that what you've learned in DiffyQ are of great use. Okay, we're not doing that for nothing. Okay. All right. With that said, any questions that anyone wants to ask? Okay. I have one more thing, but I can take your question real quick, John.
I think this is really a question of interdisciplinary involvement, because if a mathematician wants to do this, it's pretty much, it's a big math problem.
It is a math problem.
From a theoretical point of view, in terms of underlying assumptions, it might not be that necessary to talk to other disciplines, but if one is going to do this as an applied project where you're actually trying to predict what real networks are going to do under certain conditions, are there other disciplines besides mathematics and closely related disciplines like computer science?
Yes.
Are there other disciplines that are involved with something like this?
Yep. There's actually this is the network science or network studies that now it grows so fast that it becomes an independent research area, or an interdisciplinary research area, where you have people from mathematics, physics, like I pointed out earlier, business that are strictly study econometrics, psychologies that are quantitative psychologies, socialists, quantitative side, operation research that are part of industrial engineering.
It would seem that the social science and psychological science part of this would be really significant, because there's certain assumptions that are going to be made about how people behave.
Yep.
Which is largely random, I think. But still, their input, I think, would be valuable. So I guess, and I don't want to take too much time, but the question
No.
that popped up was, okay, so you have the so-called soft sciences getting involved. Their mathematical knowledge of this may not be that great. But their input is still being sought out.
There has to be collaborations. I mean, at some point in time, I think the biggest contributions from those psychologists or social scientists are more on a qualitative side, and how you quantitatively define weights between different nodes in your network. Right? Those are the things that we don't. It's not really what we are doing, but they kind of contribute on the qualitative side of it, right? And then when it gets to the math, then they, it's kind of our jobs. Yeah, yep. So, but one can arbitrarily, you know, if we are independently conduct those type of research, I think we can independently assign weight the best of our knowledge. But you know, interdisciplinary wise, I think it's we need them to be able to qualitatively define those relationships. Yes.
How much inter-community relationship building, like how much of that do you want? Like, is there a sweet spot for creating like a very efficient social media, like Facebook? Like how much between community A and community B at Facebook do they want those two communities to link up?
That's the qualitative side, I think, more in my opinion. Are you referring more of a inner community connections?
Yeah, like how strong do they want that cut? Do they?
You ideally want it to be as close as small as possible,
Okay.
because if you make a good partition in your network, you ideally don't want any cut, right? Theoretically speaking, you don't want any cut, but you obviously cannot avoid that. And in network science, usually what happens is that it's like a game playing. I create a network for you, but you don't see it. I create it through whatever the terms and the mechanism that I use. I then give you that network, and your job is to use whatever the algorithm that you come up with and give me saying that node 1 is community 1, node 2 is in community 3. I go back and I see that I reconcile with the information that I have to build a network to begin with. If you can recover exactly the topological structures of the network, it's called exact recovery. That would be the best partitions or the best techniques that one can have. But then again, the problem pops up is that in what type of scenarios do one start seeing exact recovery, and what type of scenario do one seeing almost exact recoveries, and so on and so forth. I give you the interesting stories that I promised at the beginning, but everyone's left. So. When you are, imagine that you are walking in the streets where you have two choices of turn left and turn right. I said that based on historical data, 99% when you turn left, you're going to meet an accident and you will die. 1% you would survive. If you turn right, the opposite thing would happen. What would you do? The opposite thing, by opposite thing, I mean that 99% you would survive and 1% you would die. What would you choose?
The right turn.
The right turn, because?
Higher chances.
High chance. You are now talking as a data scientist, right? You use data and that dictates your decisions. That's the same thing going for the network partitions. You decided to cut it. The moment that you cut it, you said that those two are no longer in the same community, or at least as far as you're concerned, they're not in the same community. Are they really not in the same community? So the point is, you can use scientific approach to define the relationship or interrelationship, but you're never gonna know in reality 100% that information will converge to the truth, right? Because I would argue on a conservative side that I don't know. It's no different than 50-50 for me, for example. Right? It's no different than no information. No information is, I don't know, I'm just going to flip the coin and go with the coin. But the 91%, 1% is for the data scientists to say that, okay, I now have more confidence to go with the 99% because of data. But is data all you can use or lean on to make scientific decisions? Thank you.
So it's crazy idea. Something like this comes into play when, like, nobody can successfully analyze all the cell phone traffic out there. But if we're looking for terrorists, you're looking for some way of making something stand out in terms of interactions between two people that we want to nail these two people.
Yep.
That's part of the application of something like this.
Because I've known in the operation research side, there has been tremendous research on that aspect as well. How much of that is related to modular network science, I'm not sure. But if the ultimate goal is to apply these type of frameworks into various applications, and that various applications, I think more than likely will involve what you just described. And obviously, it's already been applied into framework in application in social network and other aspects. So.
Thank you very much.
Thank you.